Hi everybody, this is Nassim, and my talk today is going to focus on how to compute the dielectric susceptibility of an anharmonic crystal. So first of all, to accomplish this, I'm going to need to use a bit of theory we saw actually in class, aka I'm going to apply linear response theory. So to remind you guys what it is, basically, if you're interested in computing how the expectation value of an observable A, let's say, changes when you apply an external field to your system, which I call F. First of all, you can write the total Hamiltonian of your system, like I did here in the bottom, as a sum of the undisturbed part, H0, and the added part, H external, where H external is of this form usually, where B is another observable, which can be the same or different than the one you're measuring, A, depending on your situation here. And when you inspect the time evolution of your operators, like we did in class, and only keep terms to the first order in your perturbing Hamiltonian, you can express your observable here in this form, where it depends linearly on your applied field, but there is a proportionality factor here, chi, which is the response function. And dielectric susceptibility is a response function, which is why this theory is so important. And we see that this response function has this specific form for arbitrary operators A and B that I used before. And this is exactly the form of a Fourier transform in time of a retarded Green's function here in this formula. And just for reference here, I included a table of a few different kinds of perturbing Hamiltonians, the V exterior. So we can have an external electric field, magnetic field, or even a temperature gradient, which all have their own associated response functions. And as you may have guessed, we're going to be interested into the second line here, where the observable that is changed here is the polarization, more specifically the electric polarization of our system. This will allow us to find our dielectric susceptibility. So here we go. If our observable is polarization, P, which is by definition the density of dipole moments, electric dipole moments in your system, so M over V, then you can write this equation where P depends on the electric field dotted into the dielectric susceptibility, chi-E, dotted because it depends on momenta, so it is a second rank tensor. And then we can plug that form of our disturbance into our Kubo formula, the general form, and we obtain this master equation here, where we see that the dielectric susceptibility from points R and S is a retarded Green's function that is of the form of a correlation function of the commutator of two dipole moment operators. And the rest of this talk is actually going to focus on computing exactly that. And because it is a Green's function, well, we can apply a lot of the techniques we saw in class to deal with that. So to do this, first of all, we need to write our full Hamiltonian here. And this is where one part of the title I didn't talk about yet comes in, aka the anharmonic part. So basically, we have the external field that has an associated potential in this form. So minus m dot E with a minus sign because it is energetically favorable for the dipole moments to align with the external field. And then H0 here, which I call H0, but is different from the normal harmonic oscillator potential. So instead of stopping to the second order in our coordinates, the U's, which are of course the lattice displacements, which characterize the phonons, I've gone to fourth order here. And this first part here, you may recognize as a standard Hamiltonian you get when you have a quadratic degree of freedom. Here, just to make sure we are on the same page, K is the crystal momentum, and J is the phonon mode. So the energy is the number of phonons in mode J with momentum K times the associated dispersion relation plus the 0-point energy. And then the other two terms, there may seem to be a lot of letters, but they're just the most general way. They're just the most general way to write these third order and fourth order terms, where you have a product of 3 U's and 4 U's with appropriate coefficients, which depend on all the summed over momenta and modes. So now that we have our full Hamiltonian, we can proceed. So we have a few unknowns here. First of all, let's look at the Phys here, which are the coefficients in the anharmonic terms of our Hamiltonian. So you can see by conservation of crystal momentum that these coefficients are proportional to delta functions of the sum of the different crystal momenta that they depend upon. And this is just physically a consequence of the conservation of crystal momentum. Another way to see it is that the terms in the Hamiltonian that have these coefficients all depend on U's, and these U's depend on the creation and annihilation operator for phonons. And you want to add the same amount of crystal momentum that you remove when you apply it to a state in your system. So these coefficients, when you do the Taylor expansion of your total potential, are all derivatives that depend on the force constants, aka the spring constants between your atoms. And another approximation we're going to do here is that we're going to express m, the dipole moment operator, in terms of an expansion that depends on these U's also. So we can do that physically because if you think about what a dipole is, it arises when there is an asymmetric distribution of charges in your system. So when you have optical modes, right, which is why they're called optical modes actually, that change the position of the ions in an asymmetric way, it does allow for the rise of these dipole moments. So there's a coupling between these dipole moments and the U's, which is written here, with again coefficients m2 and m3, the same way we did before. And by the same line of logic, these depend on delta functions of the case here. And just finally, we're assuming here that at k equals 0, there is only one photon mode that is not 0, aka that is optically active, which is why the first term only depends on U of 0, 1. So every time I write 0, 1, it means k equals 0 and j equals 1 for an arbitrary mode. And if I don't assume that, there won't be any physics problem. It'll just be a bit more complicated to add up all the contributions. But it will just take a bit more time and more space. But we've omitted that here. All right, so now that we have our definition for the M, we can plug it back in our expression, the Kubo formula for susceptibility, and we obtain this very ugly expression up here. I just wrote it so you guys can see what it looks like. You don't have to read all that. All you have to know is that it depends upon all the coefficients, the phi's and the m's, and it has different Green's function in them. So if you look at the bottom half of this slide, you have f, j's, k's, and l's, which are all different correlation functions of a different number of the u's here. And just to make sure we're on the same page again, the superscript r means a retarded Green's function, and superscript a means an advanced Green's function, which only changes the sign in front and the sign of the argument of the Heaviside function in front of the correlation function. So here we're going to assume that we know the phi's and the m's, because these can be found either through computational methods, through DFT, or by fitting simple models, like using a shell model to fit to experimental photon dispersions for materials. And there's a few people who have done that, and I'm going to talk about such an example at the end here. But I just want to make that clear so that the rest of the problem is actually just focused on finding the value of these Green's functions. And now the fun begins, and we can apply techniques we saw in class. So we're going to use diagrammatics to find all of those, pretty much. So first things first, just by the form of these functions, aka how many u's are in the left side of the comma of the commutator and how many are on the right side, you can determine the quote-unquote input and outputs of your possible diagrams here. So the F, for example, will have one photon line going in and one going out, and the J here will have one going in and two going out, or the inverse for the retarded function. So already we have a lot of information, and all we have to do is fill in the gaps. So what I've just said is illustrated in this right diagram here, where the inputs and outputs are there, where every line is a phonon line, and we just have to fill what is in each box, aka all the diagrams that contribute to this. And to do this, we have to limit ourselves to a certain order. So to do that, like we've done before, we express the total Hamiltonian in terms of a small parameter delta. And here, because we technically have two sources of disturbances in your system, aka the anharmonic terms and the coupling to the electric field terms, it may seem a bit complicated here, but just think that the first delta terms only has contributions from the phi 3 and M2, and the delta 2 terms have contributions from the phi 4 and M3 here. Don't worry, even if the numbers seem weird, they all make sense. So now that we have that, we're going to draw every possible diagram that can fit in there up to that second order in delta. And because we have an MM correlator here, for the higher functions, actually, if you look at the function, we already have M2s and M3s, for example, so it limits our amount of diagrams we can actually draw. Because we're already by default just by the outside lines at a higher order. But we're going to see all that very shortly. And as a final thing, I'm only going to draw the retarded diagrams because the advanced ones are exactly the same. And mathematically, it makes sense because you can obtain an advanced Green's function by doing an analytic continuation of a retarded one to the upper half of the complex plane. Okay, so what the paper actually did before everything, they solved for the Green's function in the same way we did in the very beginning of the semester, aka take a time derivative of your Green's function, which carries over to the time-dependent operators that are inside of your correlation function, and then you can use Heisenberg's equation to find the time dependence. But through Heisenberg's equation, you need to compute commutators with your Hamiltonian. And because our Hamiltonian is huge, these commutators are also pretty long to write and everything. So I'm just going to use the key results from that part, which pretty much translate to Feynman rules, aka how we can actually interpret different diagrams to translate them to expressions that depend on the frequency for our Green's function. So I'm not going to write all of them because some of them are pretty complicated with loops and everything, but I'm still going to talk about those when I show the diagrams. But here, okay, so when you have multiple phonon lines joining up together, making a vertex, it corresponds to an interaction between those phonons, right? So if you have 3 lines joining or 4 lines joining, you obtain a factor of phi 3 or phi 4, respectively, divided by omega squared. The omega is just consequences of the computation here. And when you have an interaction that depends on the electric field here, it'll be shown as a cross vertex. And every time you see a cross, you can count how many phonon lines go in. And then you can see, for example, that 1 line is M1, 2 lines corresponds to M2, and 3 lines to M3, right? Because the expansion of our dipole operator depended on this number of U's. And then from that, we can write expressions for all of our diagrams that allows us to find our answer. So it also allows us to determine the dependence of these diagrams on our physical parameters here. So the electric field, of course, every time you have a cross vertex. But something I want to note that is not derived here is that every time you have a closed phonon loop, aka lines that make a circle, for example, you obtain a linear time dependence in your contribution. So if you remember in the homework when we did a Green's function approach to find the self-energy of a phonon with a Hamiltonian with electron-phonon interactions, and we actually computed the Matsubara sum associated to it, we actually found exactly this because we had a diagram that is a closed for-on loop that we computed, and that did have a t dependence. So we can look back at the solutions if you want to see why specifically it has one t dependence. All right, so now I can start showing these diagrams. Just as a note, the main paper I've been following is the one written on the bottom left here by Hartmann. And all right, so the F diagrams are the one with just two for-on lines coming in and out. And these are all the options here. The paper cited down at the page has an expression for every single diagram here, but I'm just showing a few to make sense of it. So first they're ordered in terms of the order actually. And you can see, for example, that this B diagram has 3 phonon vertex here, 3 phonon lines joining, so it has a phi 3 dependence, and the M1 dependence because it has a cross with one line coming out of it. And every cross gives you one E naught dependence here. So the expression I wrote here, right, for this C diagram, as you can see, has the M1 and the MR, which are the outside and inside ones that are written here. It has a E dot M2 here because there's an X with 2 phonon lines joining in. And then there's the associated omega squared that comes with the vertex. And here is the form of the undisturbed phonon Green's function that we found in class and used before. And just to clarify, this omega squared 0, 1 is a constant here. You can consider it the analog of the Einstein frequency big omega we actually use in class. So you have all of these are the ones that are possible that don't go above delta 2 here. And right, here's another diagram I chose randomly to write the form of. Here, this is the only one here that has a dependence on phi 4 because there's 4 phonon lines coming in the same point. Sorry, actually, it's not the only one. This one also has 4 phonon lines coming in. And yeah, so 2 crosses that only have one line, so M1's here, and the associated frequency dependence in the denominator. So again, you have the E dependence, and the 3 that have loops have a T dependence here, right there. Next, the JR, which have two phonon lines coming out and 1 phonon line coming in, over vice versa for the advanced one. I'm not gonna dwell too much on all of those because the same logic applies for all of these Green's functions. But here I included a loop here where of course you have to sum over internal momenta and modes. And when you have a loop like that, the rules end up being that you need this familiar n plus 1/2 coming from the harmonic part of the Hamiltonian to sum up. And here's a more exotic one with multiple m's again, and the phi 3 in the middle here. And again, the loops have temperature dependence, and the other ones don't. And KR only has 2 possibilities. So 3 on the one direction, 1 in the other direction. Again, these are the expressions. I don't have much to say about them that I haven't already said. You can pause and look at them if you want. And then LR, which has 2, 2 on each side coming in, has only 2 possibilities to second order. And as you can see, it doesn't have any delta 1 or delta 0 possibilities, just because there's already M2s on both sides. And each M2 has a delta dependence, so you have delta squared already. So you can only add either nothing or M1s, which don't have a delta dependence easily. So yeah, you get these long expressions right there. And just from looking at these dependencies, you can draw some physical conclusions already. So first of all, most strikingly, if you've noticed that there is kind of a complementary relation between the electric field dependent diagrams and the T dependent diagrams. If a diagram depends on T, it doesn't depend on E, and the other way around too. So you see that if we didn't have an external field, if E was 0, the only terms in the second order actually here are T dependent. So I'm only showing the first subset of diagrams, but this rule applies to all of the other ones I've shown. You can go back and check if you want. And then you see that if you turn it on, all the new contributions in that order are T independent, like I've just said. And another thing that is interesting is that if, again, you switch off the field, you see that the only time a higher order dipole moment term can arise in a diagram, aka have M2s or N3s, is only in second order. And these come from the the L's and K's that already have M2s on both sides, the input and the output, as I've said. But when you turn on the field, when you turn on the field, interestingly enough, you do get some diagrams that have M2 dependence, but are only delta 1 here. Like this, for example. I've written it before because it has two phonon lines coming in, but it's only to the delta dependence. So the electric field makes the higher order dipole terms have more of an impact on the dielectric susceptibility, and of course on the following consequence of these diagrams: the self-energy effects. So pretty much, as we've done before, if you sum up all the relevant diagrams and you separate the real and imaginary parts of them, you see that these correspond respectively to a shift in the energy spectrum of your phonons, which is delta here, and a lifetime of phonon width, which is the gamma here. And again, we've done that in the same problem I've referenced with the phonon bubble diagram. But here I only added the contributions from the new parts of the Hamiltonian, aka the M-dependent or the E-dependent, same thing, diagrams. So you can see that all these terms depend highly on both the M's and the Phi's. So you get a strong coupling between the anharmonicity and the external field of a system, which is one of the main points why it's important to consider terms that are of higher order in your lattice dynamics to get accurate results for example, phonon energy renormalization or phonon width. So I'm going to talk about a few numbers here, like I've said before. So on the right here, there's a lot of data points here. Every point is an experimental data point for a neutron spectroscopy experiment done on potassium bromine at 90 Kelvin. So we see the phonon dispersion of different modes. So you see the L's and the T's, right? So longitudinal and transversal. And we have different fits, the lines with different models over these experimental data points. And the paper I'm following, actually Hartmann, considered a shell model fit, the solid line that follows these points, as a way to fit for the unknown parameters, the Phi's and the M's, which allows us to have numbers for everything. And from that, he looked at how the energy shifted, the delta I've shown before, and we see that at this 90 K temperature, with an external field at 10 to the 6 volts per centimeter, we see that the contribution from diagrams B and D here have the same order of magnitude in terms of the contribution to the shift. And this is an interesting thing because B is a delta 1 order diagram and D is a delta 2, right? It's a loop. And here the only delta term is the phi 3, which is in the middle here. But you see that the contribution from diagram B is 100 times bigger than this C diagram here. So it tells you a lot about how much it depends on your system, depending on which diagram have a better contribution on the self-energy change, and of course on the dielectric susceptibility. And yeah, so in terms of physical consequences, the electric field dependence is very important. And you see that loop diagrams that come from solely from the anharmonicity are very more important at high temperatures because they have linear dependence on T. Finally, I want to end this talk with this final slide where I'll go over a kind of a simple link between our calculation for the dielectric susceptibility of a system and an important experimental parameter in scattering experiments, light scattering experiments specifically, aka the absorption coefficient. So when you want to measure the photon dispersion, you can send photons in, and depending on the frequency, it's going to be its energy is going to be partially absorbed to excite the vibrations in there, and you can measure the energy loss of the photon going out. And how much of this intensity is absorbed depends on the absorption coefficient, which is directly related to the dielectric susceptibility. So when you measure your absorption peaks, you have a way to directly relate this result to a more theoretical result from the dielectric susceptibility. So just to summarize, if you have an electric field that is in form of a plane wave like this, the wave vector can be written as a sum of a real part k prime and imaginary part k prime prime, and this k prime prime here is exactly the absorption coefficient, because if you put it back in this expression, the i's cancel out, and you get a decay term, an exponential to the power of a real number, pretty much. And that's going to tell you how far the photon can traverse the material before it's absorbed, pretty much. So the bigger it is, the more strongly it is absorbed, and the other way around. So here's a very simple relation between the dielectric matrix or tensor and the susceptibility here. We can derive that when you write the expression for the displacement vector, right? D equals E plus P, and P I've written in terms of that. And here we're in CGS units. And if we assume, for example, a plane wave with a direction of propagation in a z direction, so k is just in the z direction, you can take twice the cross product of the electric field of this form, and you get this relationship. And then it's just a matter of solving for k here, and you just have to pretty much do a bit of math with this matrix, the epsilon, and you get this result here, where all the components of the epsilon, so 1, 1 would be in the x direction, let's say, and the 2's would be in the y direction, and 3's in the z direction. For these components of this matrix, you get this relationship, which directly relates the absorption coefficient and the components of this epsilon tensor, which you can get from a calculation right there. So I hope this talk was instructive, and I hope some equations were not a bit too big or distracting. And yeah, so if you have any questions, I'm glad to answer them. Thank you for listening.